Okay, so this is my programmable Redstone computer. It works in Minecraft 1.16 without any mods or command blocks. So first I'm going to do a quick tour of all the components, and then I'll run some programs to show you how it works. So right here we have the instruction memory, and it uses these locking repeaters, which are 5 blocks apart. So it's not the most compact design in the world, but it's good enough for now. Now this component can store 16 instructions, and this other instruction memory component can store another 16 instructions for a total of 32 instructions. Now the input, you'll see that the width of an instruction is 11 bits, which is kind of an unusual width for an instruction, but it's really nice because it gives me a 3-bit opcode and an 8-bit immediate value. And the largest values that this computer can operate on are 8 bits, so it works out pretty nicely. Now the inputs and outputs of the instruction memory go out onto the instruction bus. You'll note that I separated the instruction bus from the data bus, which is above us, and this is because originally I was going for a Harvard execution model design, but the control logic for that proved kind of difficult to design, and to be honest, I didn't really know what I was doing, so eventually I decided to scrap that idea, but I still kept this like separated design. And it's still really nice because it allows my program counter, which is this component right here, to be the same thing as the instruction memory address register. So I don't need to have a extra fetch clock cycle every time I'm fetching an instruction, because I don't need to write data from the program counter to the instruction memory address register, because they're the same thing. So the program counter is implemented with a register and a modified like full adder circuit, which can just increment it. And the outputs of the program counter go into these, the address outputs of the program counter can go into these decoders, these purple decoders, and this is a really nice design by Nubasaurus, which keeps the inputs really close together and also the outputs really close together, and there's a pretty long distance between repeaters, so it's a really nice design. So these decoders take in the addresses from the program counters, as well as a read, write, and clock signal. So the read control signal is used to output instructions onto the bus, and then the write and clock signals are used to write instructions into memory. So that's, if you're in programming mode, you can use those signals to program the computer to do whatever you want. Okay, so on the other side of the instruction bus, we have the instruction register, which can output its values onto the bus as well. For example, if you want to output the jump, the new jump address, then it would come from the instruction register, and then it also outputs its values, or it can output its values onto the data bus. For example, if you're doing a load immediate. Now it also at all times outputs its contents to the control logic, and the control unit is implemented as a mealy state machine, which is quite nice because it means I only need 4 states to control the whole computer: a fetch state, a decode state, an intermediate load store state, and a halt state. So this is the next state decoder right here, and it takes in the 2 state bits, a continue signal, which is used to break out of a halt, and the 3 opcode bits from the instruction, and it'll decide what the next state should be. Also, the instruction is input into the execution decoder, as well as the continue signal and the current state, and all of this together is used to decide what main control signals need to be output every clock cycle for the operation of the computer. So it's quite long. So this part of the decoder outputs the control signals for all the regular operations, and then this part till the end outputs control signals for the ALU operation. And so for whatever ALU operation we want to do, so for example for add or subtract or whatever we want to do, this output gets fed into this encoder. And then the encoder outputs the actual control signals into the ALU. And the reason we need this sort of system is because some ALU operations take multiple control signals to do. So for example, if we wanted to do an OR operation on the ALU, then that would be a combination of the XOR as well as AND control signals. So this encoder allows that to happen. So these control signals go up into the ALU, which is this component, and it's also a really nice design by Nubosaurus, and I added a few extra control signals and operations to make it even more powerful, which I'll leave on the screen right now. Now the ALU also outputs 4 flags, which are the 0 flag, sign flag, overflow flag, and carry flag. And those are like the 4 main flags that you want an ALU to output anyway. So now this is the flags register, so it outputs it into the flags register and it gets stored there. And then these 4 flags go into yet another decoder, which is this one. And this decoder takes in as inputs the 4 flags, as well as the 3 bits that can be used as a jump code. So, if we have 4 flags, we want to jump on if any of those flags are set, or if any of those flags are not set. And then jump code decides which of those 8 combinations we actually want to jump on. And then if any of those are true, then it gets output over here into this line of the execution decoder, and if the jump condition is true, and also the actual instruction is a jump instruction, and we're in the correct state, then the jump control signals get output, which are one of these. So above the execution decoder, we have 3 more decoders, and these are used for basically deciding which register we want to do. So if we have like a register, like a transfer operation, like a copy from one register to another register operation, then the execution decoder will send the correct write and read signals to the correct registers, and then they also take as inputs bits from the instruction, which decides sort of what registers we want to operate on. Okay, I think that's pretty much it for the control logic. This is the ALU. So the ALU takes inputs from the A register over here and the B register over here. And you can see it's actually quite a long distance to be input into the ALU. I'm not really happy with how this design, how this part of the design turned out, because I really would have preferred a shorter distance. It really slows the clock down quite a bit, I think. But anyway, so the ALU takes in those inputs from the A and B register, then the control signals decide what operation it performs, and it outputs it onto the data bus. On the data bus, we have the 4 registers of the 4 main registers of the computer, which is the A and the B register, and they can read and write onto and from the data bus, and also, as we saw, they constantly output their contents to the ALU regardless of the control signals. So past these 2 registers, we have the display register on this side, and basically it works the same as the other registers, except it always outputs its data regardless of any control signals to the output. So that's how we can get the output from the program. Also, there is, on the other side of it, there is the input register, which is this thing right over here. And this is how we can get data into the program while it's running. And basically the way it works is, if the program is halted, then when we press the continue flag on the console, which is over here, so when we press the continue signal on the console and the program is halted, then whatever contents we have on these bottom 8 bits get read into the instruction register, and then we can move that data and do whatever we want with it. So it's kind of like, there's no interrupt handler or anything like that, but this is one way that you can get data into the running program. You can also just get data in with like load immediate instructions and things like that. Okay, so past the registers on the data bus, we also have the data memory. And again, there are 16 bytes of memory on this side and 16 bytes of memory on that side. And it reads and writes onto the data bus as well. and it's controlled by the data memory address register. So, if whatever data address we want to read or write to, that data gets stored into the data memory address register, and then again, we have the same type of deal with the decoders. You have the 5 address bits, as well as a read, write, and clock signal into the decoders, and when the correct combination is set, then the data memory will read or write at the correct address. So I think that's pretty much all I wanted to show. I think that's all the components. Okay, so right now I'll show a couple running programs just to show you how everything sort of works. There's also the clock, of course, and it's a pretty slow clock. It's 50 redstone ticks per cycle, which isn't great, to be honest. I really was hoping to be able to design it to be stable at much faster clock speeds, but oh well, that'll have to do. Also one more thing is that there's no unconditional jump, which is kind of annoying, but I didn't really have room in my instruction set to put an unconditional jump, and when I was designing it, I thought, that wouldn't be a big deal, who cares? But when I was actually testing the computer with different programs, I realized that it's actually quite useful to have a unconditional jump. And so basically what I did is I added a ALU none operation, which is right here, and what it does is it produces no output, but it's guaranteed to set the 0 flag. And so if we want to have an unconditional jump, we would have that instruction, which always sets the 0 flag, and then we can have a jump on 0 instruction right after it. And that sort of simulates an unconditional jump, but the annoying thing is that it does take 2 instructions, which isn't great. Like, it really should just take 1, but oh well, lesson learned, I guess. Okay, so the first program that I want to run is the hello world of Redstone computers, and this is the Fibonacci sequence. So I'll write that in right now. So at address 0, so right now we're in programming mode, so I can input instructions to the computer. So at address 0, I'm gonna put in the load immediate command, and it'll load in a 1. So the load immediate command opcode is 010, and then the value that we want to load in is a 1 at instruction memory address 0. And so then we will press the continue thing, and when it turns off, that value will have been written in. Okay, and now we go on to instruction memory address 1, and this will be a transfer A to B command. So the opcode for transfer is 100, and then from A is 001 to B is 010, and the last 2 bits don't matter. And then again we press continue and write that instruction into memory. Okay, so I'll speed this part up, but you can see what I'm doing. Okay, so now I've written in the Fibonacci sequence program into memory. and we can run it. So what we should do is leave programming mode. So now that starts the clock, and then we can reset. And hopefully it should start counting. It'll start at 1, and then it'll go to 2, and then 3, and then 5, and so on. And then when it reaches the max value that it'll do, which is in this computer 233, it'll do the addition again, go to 377, which will set the carry flag, and then it'll reset right back to 1. So it'll never give bad data. It'll just keep on looping forever. So it'll take a while because it's already at 1, so nothing will change for the very first output, but then eventually it'll go on to 2. And then, yeah, it'll never halt because it's going on forever. So something interesting with this program is that it takes 3 instructions to write the next value, to output the next value. So there we go to 2. And since the clock is stable at 50 redstone ticks per cycle, that comes out to be 5 seconds per cycle. And since all of the instructions in this program take 2 cycles, it takes 10 seconds per instruction. And since there are 3 instructions between outputs to the display, it takes 30 seconds between between the next number being output. So there we go, that's 3. And now the next one should be 5 eventually. Yeah, I'll show a few of these, and then you can if you want, I'll leave a world download in the description, and you can play around with the computer if you want. There we go, that's 5. And after that it will be 8, and then 13. So yeah, as you can see, it is really slow. I think even for like Redstone computer standards, it's pretty slow. I'm not quite sure why it's this slow, because I looked at some of the longest paths that data needs to travel, and it definitely didn't look like it takes 50 redstone ticks to do it. There we go, that's 8. But for some reason, if you go any slower than that, it just stops working. So I'm not sure. There might be some data travel that I'm not taking into account. But anyway, I think this could be solved in the future with a much cleaner design. You can see I have a lot of like weird wires running throughout the whole computer. And they add distance, so especially the control signals, I didn't even consider them when I was planning out the design. I sort of, yeah, that's 13. When I was planning out the design, I didn't even think about how the control signals would work. I planned out the bigger components and made sure that those were nice and compact and close together where they needed to be. But the control signals, I just put wherever I could fit them by the end of the build. So I think, with taking into account the control signals a little bit more, would have been a little bit wiser. Yep, that's 21. Okay, well, you get the idea. So it just keeps counting up, and when it would get to after 233, it'll just reset back to 0. Okay, so now I'll run the second program. And the second program I want to show is a multiplication program, and this will actually take advantage of the input capabilities of the computer. So I'll program that now, and then I'll talk about it after. Okay, so there we go. I've programmed in the multiplication algorithm. And the computer isn't really designed to do multiplication, but we can still do it by doing repeated addition in software. So, okay. Now we'll leave programming mode, start the clock, and reset back to the start of the program. So the first thing the program will do is clear the display, and then it actually uses the display register as a yeah, there we go, clears the display, and it uses the display register as a working register for the program, but I designed it in such a way that I designed the algorithm in such a way that the display register actually ends up counting down until the program will output the correct result. Okay, so yeah, the first thing that the program does after it clears the display is it halts, and that lets you input the first number that you want to multiply. And this algorithm works on 2's complement, and the first number must be positive because that's the number that we will be decrementing down. So I'll put in 3. And it's nice to make the first number the smaller number, and then we'll press continue, and this will unhalt the computer but also write in this value into the input register. And it's nice to keep the first number small because that's the one that'll be sort of counting down. So, you know, if we're doing 3 times, I don't know, 8, for example, then, you know, we want to go 8 plus 8 plus 8 instead of, you know, 3 plus 3, 8 times. Okay, so now it's halted again and it's ready for our second input. I'll just do 8. And then continue. So it'll end up doing 3 times 8, which is 24. So that'll be 16, so that the correct output should be eventually when it halts. So right now it'll give different data, but when it halts, the correct output should be 1, 2, 4, 8, 16 plus 8, so these two for 24. So you can see it right now, the value is 2, and that's because it's 3 minus 1. So right now it's sort of telling us that it's going to do the first addition right now. And the second number can be negative as long as it's in 2's complement, or it can even be 0 and it will still work, but the first number needs to be positive in 2's complement to work. So while it's counting, the biggest limitation right now with the computer is definitely the clock speed, and you know, that's something that I'd like to improve upon in the future, and I can do that by, you know, designing the components to be faster, but more importantly by, you know, designing the overall layout to be slightly, you know, more intelligently designed so that there's less signal travel between components, not just within components. I'd also like to experiment with pipelining. That seems really interesting, and it seems like it would increase performance a lot as well, and maybe even branch prediction. That seems really interesting as well. I'm not quite sure how, you know, I would do that yet, but, you know, that's something I'd like to experiment with. Also, there's no concept of a stack on this computer, whether in hardware or in software. That's also something I would like to play around with. That would let the computers, you know, write more complicated programs and do more complicated things rather than just, you know, what I've got so far. The Harvard execution model seems interesting as well. I'd like to experiment with that more just to get more usage out of the computer, because right now most instructions take 2 clock cycles, which will be so right now it's 0, and then the next value that it outputs will be the correct value, and then it will halt. Right now, like, half the computer isn't ever being used at any given point because the fetch cycle only operates, you know, on this part of the computer, and then the execution cycle operates on this part of the computer. So half of the computer's resources are being wasted. And there we go, that's 24. And then the computer will eventually halt the program, and that'll be that. So it actually halts it back at the first input. So we could actually input like a second. Once it halts, we could actually input like another first number and another second number, and it will do the multiplication all over again. So it jumps back to the start and halts there. Yeah, there we go. So yeah, I think that's pretty much it. I'll leave a world download in the description and a datasheet for how you can use the computer in the description as well. Thanks for watching.